Intermolecular forces. Before I explain in details on intermolecular forces, let's look at the types of forces first. There are two types of forces, intramolecular forces and intermolecular forces. In this subtopic, we are going to focus on intermolecular forces only, but I'm going to explain the general of types of forces. Intramolecular forces is forces that hold atoms together in a molecule. So in making a molecule, there are groups of atoms or several atoms grouped together in a molecule by intramolecular forces. The types of intramolecular forces are ionic bond, metallic bond, covalent bond. These are the examples of intramolecular forces. Intra means inside the molecule. Inside the molecule, between the atoms to form the molecule. Intermolecular forces, subtopic 4.4, it's about attractive forces between particles. The particles are atoms or molecules or ions. So this intermolecular forces is outside the molecule. So forces of one molecule with another molecule, or one atoms of another atoms, or between the ions itself. So under intermolecular forces, we have two types of intermolecular forces, hydrogen bond and van der Waals forces. These are two types of intermolecular forces. And under van der Waals forces, we have dipole-dipole forces and dispersion forces, or another name for this is London forces. So intermolecular forces are hydrogen bond and van der Waals forces, and under van der Waals forces we have dipole-dipole forces and dispersion forces. Focus on van der Waals forces, these two. Focus on this. Focus here, the van der Waals forces, dipole-dipole forces and London forces. For dipole-dipole forces, it is attractive force between polar molecules. So you have a polar molecule and another polar molecule. If there are attractive force between these two polar molecules, it is dipole-dipole forces. London forces caused by the motion of electron in a molecule or atom. These London forces exist between non-polar, and London forces also exist in polar molecule. So basically, London forces exist in any particles. Whether it's polar or non-polar, it exists. The London forces exist. But for dipole-dipole forces, it's only for polar molecules. The more polar the molecule, the stronger the strength of its dipole-dipole forces. For London forces, forces are weak but exist in any particles, whether it's polar or non-polar. It's London forces. How London forces form? This is the example between non-polar atom and non-polar atom. So this He atom and He atom is non-polar. The electrons are distributed uniformly around the nucleus. That's the first process. No attraction yet. Electrons are distributed uniformly around the nucleus. At any instant, there may be more electrons on one side of the nucleus, because the movement of electrons within this atom is random. So probably at some time, this side is more negative on the other side. This is what you call instantaneous dipole due to the random movement of electron. Electron probably be more on the left than on the right. So that's what we call instantaneous dipole. And when the atoms are close together, the instantaneous dipole in one atom induces a dipole and its neighbors. So when they are close together, it induces a dipole and its neighbors. It means the instantaneous dipole atom, this atom that has slightly negative pole and slightly positive pole, that's why we call it dipole. It means this instantaneous dipole atom influences the atom that is close with it to be like this one. So when they are close together, this atom is influenced by this atom to be dipole as well. When it becomes dipole, the name of this atom is induced dipole, because this atom is being induced by the instantaneous dipole atom. Attraction between instantaneous dipole, induced dipole forms London force. So this is London force. When this becomes induced dipole, the charge, the slightly negative charge, this charge must be different from the charge with this one, because they want to be attracted. So if the right side of this atom is slightly positive, this induced dipole on the left side must be slightly negative for these two to have London force. So this is how London force form between nonpolar, because we know nonpolar has no slightly negative or slightly positive. It becomes instantaneous dipole by the random movement of electron. The electron move randomly, at some point making it slightly negative on one side, slightly positive on one side, and it influences other atoms to be like it as well. And then when both becomes dipole, they will attract. Next example is between nonpolar and nonpolar molecule. Previously we looked at the atom. Now it's between molecule. Again, the electrons are distributed uniformly around the nucleus. So this chlorine and chlorine, same electronegativity, so the electron distributed uniformly. At any instant, due to the random movement of electron, at some time, electron probably may be more on the left side compared to on the right side, making this molecule, you call it instantaneous dipole. It's dipole because it has two poles, one slightly positive and one slightly negative. So this is instantaneous dipole molecule. When the molecules are close together, this instantaneous dipole induces dipole to its neighbors. Means this molecule influence molecule B to be like molecule A. And then the side by side must be negative and positive, means they must be in the opposite charge. So if here is delta plus, this side must be delta minus for them to be attracted by London force. Attraction between instantaneous dipole, induced dipole forms London force. So this is the example between molecules. Strength of London force. Two factors to determine the strength of London force. First is polarizability or size. Second is molecular shape. So polarizability, the strength of London force depends on the number of electrons. We know that if the molecule is big, means there is more electron in that molecule or that atom. If that atom is big, means it has more electron. Molecules with bigger size or larger molar mass has more number of electron. So the polarizability of molecule increases if it has bigger size or if it has more electrons. So that molecule or atom will have stronger London force. Second factor, molecular shape. The larger the surface area of the molecule, the contact between molecules increase the stronger the London force. Effect of polarizability on boiling point. We have here example methane, ethane, propane and butane. Methane, ethane, propane and butane all are non-polar molecule, all with C and surrounding atom H, central atom C, surrounding atom H, no lone pair at C. So all of them are non-polar molecules. London forces exist between their molecules because they are non-polar. We know that in non-polar molecule there are London forces. The strength of London forces is directly proportional to the polarizability, means N-butane has the strongest London force because it is the biggest molecule. More energy needed to overcome the London forces between butane molecules. So that's why if you look at the temperature for boiling point, it's negative 0.5 for N-butane. For methane, negative 161.5. Ethane, negative 88.6. So it keeps increasing. The boiling point keeps increasing. Boiling point means the energy required to overcome the London forces. So more energy required to overcome the London forces in butane because butane is the biggest. Thus, butane has the highest boiling point. Effect on molecular shape, we can look at in butane and 2-methylpropane. Both have the same chemical formula, C4H10, C4H10, but the molecular shape are different. Butane and 2-methylpropane are non-polar molecules and have same molecular size because they are C4H10 and C4H10, so same molecular size, but they have different molecular shape. The surface area of butane, this one, is larger than 2-methylpropane. Here 2-methylpropane surface area is smaller because this C and this C block this carbon. Any molecule or any atom that want to approach this carbon is blocked by this and this carbon, making, or we say, this 2-methylpropane has less surface area. So that's why this butane has bigger surface area. Thus, it can form more London forces between molecules in butane. Bigger surface area can form more London forces. More energy required to overcome the stronger forces. When you have more surface area, bigger surface area, the London forces is stronger. When the London forces is stronger, you need to have more energy to overcome the forces, mean it has higher boiling point. The boiling point of butane is negative 0.5 degrees Celsius. The 2-methylpropane negative 11.7 degrees Celsius. Thus, butane has the highest boiling point because it has bigger surface area, even though they are in the same size or the same molecular size. London force versus dipole-dipole force. Generally, dipole-dipole force that exists between polar molecule is stronger than London force, which exists between non-polar molecule and also polar molecule. So generally, dipole-dipole force is stronger than London force. However, if the non-polar molecule is larger than the molecule polar with dipole-dipole force, the non-polar molecule has stronger London force. If the non-polar molecule is larger than polar of dipole-dipole force, it means the polar molecule is small. So the London force will be stronger than dipole-dipole if non-polar molecule is larger than polar molecule. For example, this one, CHF3 polar molecule, CCl4 non-polar molecule. If we don't consider the size, polar molecule has dipole-dipole force, non-polar molecule has London force. This one, it also has London force, but it has dipole-dipole force as well. So generally, dipole-dipole force is stronger than London force in nonpolar. But the boiling point shows that for CCl4 is higher than CHF3, means the London force in nonpolar is stronger than the dipole-dipole force in polar molecule. This is because if you look at the weight or the size, means this CCl4 is bigger than CHF3. Even though CHF3 has two types of forces, CCl4 only has one type, which is London forces. The London force is stronger than London force and dipole-dipole in CHF3 because the nonpolar molecule is bigger. Next is hydrogen bond. Hydrogen bond is the force between polar molecules which have these are two conditions. First one, partially positive hydrogen atom bonded to highly electronegative atom N, O or F. So this hydrogen atom bonded to N or bonded to O or bonded to F, hydrogen bond will exist when it follows this condition. And second condition is partially negative lone pair electrons on N, O or F of another molecules. These are the example for hydrogen bonding in ammonia, acetic acid and methanol. In ammonia, 3 ammonia molecules, 1, 2, 3. So for this one molecule, the hydrogen atom is bonded to the N. This one, in acetic acid, hydrogen atom is bonded to O. Another one, hydrogen atom is bonded to O as well. Okay, for this, in ammonia, the hydrogen atom bonded to N, the hydrogen bond must be the hydrogen that bonded to N, O or F, and the hydrogen bond will exist between that hydrogen and N, O or F of another molecule. So this is the hydrogen bond. This H and N is not hydrogen bond. The hydrogen bond must be for different molecule. This hydrogen has hydrogen bond with nitrogen of different molecule. The first condition is the hydrogen need to be bond with nitrogen, oxygen or fluorine. The second condition, the hydrogen that bonded to nitrogen, oxygen or fluorine must have lone pair. Same goes for this one. The hydrogen that bonded to nitrogen, oxygen or fluorine, hydrogen bond is between that hydrogen and N, O or F. So this is the hydrogen bond. In acetic acid, hydrogen bonded to O, hydrogen bond exists between that hydrogen with oxygen which has lone pair electron. Same goes to this one. And in between methanol, hydrogen bonded to oxygen. This hydrogen that bonded to NOF means here it is bonded to O. This hydrogen will make hydrogen bond with NO or F. In this case, it's O with lone pair. Second condition. So that is hydrogen bonding in methanol. Same goes for this one. Strength of hydrogen bond, electronegativity of the element, and number of hydrogen bonds. These two are the factors that determine the strength of hydrogen bond. Hydrogen bonding in H2O is stronger than NH3 because O is more electronegative than N. So when the molecule has oxygen and another molecule has N, so the hydrogen bond between the molecule that has O in it is stronger than hydrogen bond than the molecule that has nitrogen in that. Secondly, number of hydrogen bonds. Although F is more electronegative than O, so suppose hydrogen bond in F is stronger than the hydrogen bond that molecule has O in that, the boiling point of HF is lower than H2O. So here with F more electronegative than O. So suppose this hydrogen bond is stronger than the hydrogen bond is in water, but if you look at the boiling point, HF boiling point is lower than H2O because the molecule of H2O can form more number of hydrogen bond than HF. So that's why the HF boiling point is lower than H2O even though F is more electronegative than O. This is the molecule of HF and another molecule of HF. There is one hydrogen bond can be formed between the atom F in one molecule and atom H of another molecule. But if you look at water, you can form, if there are 3 water molecules, you can form 2 hydrogen bond. One molecule can form 2 hydrogen bond with another water. But for this one molecule can only form 1 hydrogen bond. One molecule water can form 2 hydrogen bond if you have available 2 water molecule. So that's why the boiling point of HF is lower than H2O because H2O can form more hydrogen bond than HF. Effects of hydrogen bond on boiling point. We focus on group 14, 15, 16 and 17. So I'm going to explain first for group 14. We look at CH4, CiH4, GeH4 and SnH4. So these are the molecule in group 14, CSi-GeSN. The boiling point increases gradually from CH4CiSH4 GeH4 to SnH4 because the molecular size of hydrides increases when going down the group. So this is all group 14. Going down the group, we know that the size is increasing, the size of the atom increasing. So the molecular size of the hydrides also increases. Type of intermolecular forces exist in the hydrides is van der Waals forces. So these are the intermolecular forces. Types of intermolecular forces, van der Waals forces. There's no hydrogen bond because this C is not NOF. Hydrogen bond only exists when there is electronegative NOF atom in that molecule. But CSi-GeSN is not NOF, so this molecule cannot exist. Hydrogen bond cannot exist in this molecule. So the type of intermolecular forces between them is van der Waals forces. That's for group 14. And for group 15, 16 and 17, the boiling point for hydrides is abnormal. So it's not like group 14. It's not keep increasing. NH3 high boiling point suddenly decrease and then increase again. It's abnormal due to the existence of hydrogen bond in NH3. For group 15 here, the green dot, group 15, only NH3 has the hydrogen bond. PH3 does not contain hydrogen bond. ASH3 cannot make hydrogen bond. SbH3 cannot make hydrogen bond. So only NH3 can make hydrogen bond. Hydrogen bond only exists for NH3. So that's why the boiling point of NH3 is higher. This is due to the hydrogen bond is stronger than van der Waals forces. So van der Waals forces, we know that we have dipole-dipole force and London force. So this PH3, ASH3, SbH3, only van der Waals forces exist. Boiling point of NH3 higher because NH3 has hydrogen bond. Hydrogen bond is stronger than van der Waals forces, so that's why the boiling point of NH3 is higher than the other atom in the group. Same goes for group 16. For group 16 and 17, so this group 16, HF, HCl, HBr, HI, H2O, H2. This one, the yellow one is group 17, the blue dot is group 16. Yellow group 17, blue group 16. So boiling point, the reasoning are the same, abnormal because only H2O exists, hydrogen bond only exists in H2O if you compare with H2S, H2SE, H2TE. Same goes for this one, hydrogen bond only exists in HF if you compare with HCl, HBr and HI. Then now we focus on these three. Boiling point, if you look at the graph, the boiling point of NH3 is lower than HF, and then HF boiling point is lower than H2O. F atom is more electronegative than O atom. The hydrogen bond between HF molecules should be stronger. So suppose this HF has stronger hydrogen bond, so the boiling point is supposed to be higher because it has stronger hydrogen bond, because it's more electronegative. But H2O can form more hydrogen bond per molecule. One molecule H2O can form more than one hydrogen bond. One molecule HF can only form one hydrogen bond, but for H2O it can form more than one hydrogen bond, making the number of hydrogen bond in H2O higher. Thus, H2O has higher boiling point. Hydrogen bond in NH3 molecule is weaker than HF because the electronegativity of N is less than F. Thus, the NH3 has the lower boiling point. So each comparison has its own reason. When you compare between HF and H2O, the factor is about the number of hydrogen bond. But when you compare the NH3 and HF, the factor is the electronegativity of N compared with F. So each comparison has different reasoning, depends on which molecule do you use for comparison. Next, the effects of hydrogen bond on solubility. Polar molecules tends to dissolve in polar solvent. So when the molecule is polar, the type of the molecule polar, it will dissolve in polar solvent. If the molecule is non-polar, it will dissolve in non-polar solvent. Polar molecule cannot dissolve in non-polar solvent. It must be the same. Polar molecules dissolve in polar solvent. Water, we know water is polar molecule, even though this molecule has same surrounding atom, but oxygen has lone pair, so that's why water is polar molecule. It is able to form hydrogen bond with polar solvent. Our polar solvent example here, dimethyl ether and ethanol. So it can form water, can dissolve in ethanol, water can dissolve in dimethyl ether, because water is polar molecule, dimethyl ether is also polar solvent. Here water polar molecule, ethanol polar solvent. Thus, polar molecules can form hydrogen bond with water, tends to be soluble in water. If you want to know whether that molecule is soluble or not, you have to check the type of the molecule and the type of the solvent. This one, water can dissolve in dimethyl ether, depends on the type and depends on whether it can form the hydrogen bond or not. If it can form hydrogen bond, means it is soluble. If it cannot form hydrogen bond, means it's not soluble. So that's how you check the solubility with water. If you want to check solubility of dimethyl ether, does this dimethyl ether can form hydrogen bond with water? If yes, then dimethyl ether can be soluble in water. Same goes to ethanol. If the ethanol can form hydrogen bond with water, means ethanol is soluble in water. That's how you check the solubility. Next, effects of hydrogen bond on density of water. In most substances, the molecules in solid are more denser than its liquid. Usually, solid is more denser than liquid. But it's the opposite for ice. The density of ice is less than water. Ice is solid. Water is liquid. But ice is less dense than water. It results from the geometrical arrangement of hydrogen bond in water. This is water molecule, one water molecule. And the whole thing is the geometrical arrangement of H2O in the solid form. When it is arranged like this, when the water molecule is arranged like this, when it is in solid form, it causes the ice has an open hexagonally shaped crystal structure. Means you have open air between the water molecule, open space between the water molecule. So this arrangement, this geometrical arrangement cause the solid water or ice less dense than liquid. This is liquid water. There is no open space or air in between the molecule of liquid water. This is the water molecule. It forms the hexagonally shape between all the water molecule, causing open air. This open air, open space, cause the ice is less dense than water liquid.